If you go on Google and you search for Posites, you're going to get a Nike shoe. And I had that on the screen a few moments ago. But if you look for Posites in the NCAT lab or NLab, you find a nice article. And really, in this talk, I think I'm not going to say much that is new. And as a matter of fact, in thinking about this, this is a adaptation of a chapter in topos theory to partially ordered sets. And I feel like perhaps what I'm doing is describing how to re-engineer a Learjet in order to build a roller skate. So it's a realization of an idea from topos theory that is complicated and has important applications, and it has some interesting properties, though, in the case that we're looking at. And as a matter of fact, this is the motivation for thinking about this. First of all, many years ago, I wrote a paper called Kappa Frames, and actually, at the time that I wrote that paper, I was trying to understand how to do this re-engineering that I just talked about, and found I didn't have a good guide to the category theory that I understood, but I knew enough about sets to recognize that sets of regular cardinality had the properties that were needed. Now, since that time, some people have this idea of a partial frame has circulated around, and Annalisa Schauer and what's first name? Schoenfurt. Yeah, they have written several papers on this, and I've looked at those, and but I'm not sure that the final word has been written on what this should be. Second thing that I was concerned about was finding a useful representation of homomorphic images of semilattices, and especially how to describe semilattices that are presented by generators and relations. There's a nice application of this in Fred Verung's paper on the representation problem for distributive semilattices, where he uses essentially a term rewriting system. But I'm wondering, and I don't know whether or not the kinds of presentations that we can create of semilattices here could be applicable to this. So here I'm talking about some hazy ideas that I'm hoping to explore. Finally, there are some classical constructions in semilattices, namely the injective hull and the distributive envelope or the distributive envelope that fall into this, that can be handled in this setting. And so putting these constructions into this setting seems something worthwhile. Okay, so first of all, much of this talk is trivial and would be of no interest to a veteran category theorist who would, I think that you're just running through the multiplication table for me. But on the other hand, people that are not people other than Peter Johnstone, right, need some orientation. Okay, so first of all, any poset can be viewed as a category. The objects of P are the elements of P. Every Hom set is either empty or contains a single element, and it contains one element if A is less than or equal to B. A function between posets is a functor if and only if it's all right. Given a function between posets, It's a functor if and only if it preserves order. And another thing to note is that the categorical product, or respectively the coproduct of two elements in a partially ordered set, if it exists, is the category, or in a poset considered as a category, the categorical product or coproduct of two objects exists if and only the greatest lower bound exists, and that's the greatest lower bound or the least upper bound. Okay. Semilattice then is a set associative idempotent commutative operation having an identity element, and semilattice morphisms preserve that element. In a joint semilattice, the operation is denoted by sup, and the identity element is 0. The canonical order is defined by A less than or equal to B if A sup B is B. And in this order, A sup B is the least upper bound of A and B. So as a category, a joint semilattice is co-Cartesian. And then since reflections have always been, categorical reflections have always been a object, but something that I've always had a lot of fondness for. Well, in a joint semilattice viewed as a category, the function that takes x to A sup x for a fixed A in x, which takes S to the upset of A, is a categorical reflection. That is, for any morphism, that is, there's a unique morphism from X. See, in this setting, uniqueness is given. You never have to prove uniqueness. You always have it. But so existence is the only thing that matters. But if there's a mapping from X to A sup X, or there's a unique mapping from X to A sup X, and this has the universal mapping property that if given any mapping from X to Y, that is, if X is less than Y, then there's a unique mapping from A sup X to Y. That is, A sup X is less than or equal to Y. But Y is greater than A and Y is greater than X, and A sup X is less than or equal to Y. So it's saying this, familiar things that are could be introduced at a very elementary level, but saying them in the language of category theory, and will look more impressive in the case. Okay, now what I want to do now is to present some definitions from Peter Johnstone's book, Sketches of an Elephant. Chapter C, section 2. My goal ultimately is to interpret these definitions when the category in which they're implemented is a semilattice. And when we do that, they become extremely simple. Now this section, what I'm going to talk about for the time being is mainly for motivation. The definitions are very complex. And if you haven't seen the definitions before, then for the next 10 minutes, I'm going to be completely non-understandable, right? Completely opaque, I guess. So bear with me. Maybe some of these things will ring a bell or make sense, but I'm not trying to communicate anything other than an impression at the moment. Now, sites, which we're working toward. The definition of a site is at the bottom of the page. Sites are useful for constructing sheaves. That's the purpose they were created for by Grothendieck. But here are the definitions from what Johnstone has done, incidentally, in his book, is presented these in the most conspicuous manner that I've ever seen. So you can, if you're willing to put in a few days reading and scratching your head, reading this section is a great way to learn about these things. All right, so a coverage on a category C is an assignment. All right, what it does is to each object of C, it assigns a collection to U of morphisms with codomain U, which are called the T coverings of U. And the only condition that's required in order to be able to construct sheaves is this refinement property. That is, if F sub I is a covering of U and V is a and G is a mapping of V to U, then there's a covering of V that each element of which factors through some element of F. In other words, later on we'll rephrase this and it'll make a lot more sense. And then this is the definition of what a site is. Okay, now the information given in this definition suffices to for the purpose, but it creates a heavy demands on proving that constructions work. So we can enhance the definition in a manner that makes it easier to perform constructions. And these are the ideas here. First of all, a sieve on an object of a category C is a family of morphisms with codomain U, such that any sieve on an object U of C is a family of morphisms with codomain U, such that F composed with G belongs to that family whenever F belongs to that family and the composite is defined. So you would think of an element F in R being a mapping from V to U. And if I had another mapping from something to V, then the composite of those two things would belong to the sieve. Now, this idea of a sieve, right, later on, we'll see in the context of Posites, just becomes a downset. Right? See, that's obvious. Now, a Grothendieck coverage is, and this, here we've enhanced the definition in a way that makes the constructions a lot easier. A Grothendieck coverage is a coverage T in which all covers are sieves. And first of all, the maximal sieve on any object is a covering. And there is another refinement property here. Let's see. Or there's a local property, all right? That is if a we'll see this in the interpretation of this later, and it'll make more sense at that point. All right, and then we want to define a morphism of sites. Right? A morphism of sites is a functor, which is cover preserving. And the idea of cover preserving is obvious, right? If R is a cover of U, then the images of the elements of R under the functor are a covering of the image of U. A morphism of sites is a cover preserving functor that satisfies some additional conditions, and those are technical, and I'm not going to talk about them now. All right, well, let's specialize these definitions to Posites. This section simply presents the material from NCATLab, and you can look this up, and I refer you to it. It's a nice, and it's primarily this is by Toby Bartels, I think. This doesn't, I don't know of another source of this material, and this is a very nice presentation of it. All right, well, the coverage on a poset P is an assignment T, which to each element U of P assigns a collection TU of subsets of the downset of U, they're called covers of U, such that if given such that if I have a particular cover and I have an element less than U, then there is a cover of that element V that refines U. Right? If V is in U, then any cover of U has a refinement that covers V. We say that S Right, a collection of elements in a poset is a refinement of R, a collection of elements in a poset, if every element of S is less than or equal to some element of R. We don't have to have that. All right. So a poset equipped with a cover is called a posite. A sim on an element U of a poset P is simply a downset contained in U. Very simple. And a Grothendieck coverage on a poset P is a coverage T in which all covers are downsets. And for each U in P, the downset of U is a cover of U. And if R is a cover of U and S is a downset contained in down U, and for each V and R, S contains a cover of V, then S covers U. So, right, so we're saying that if S locally covers, if S covers the elements of a cover of U, then S covers U. Right? Clear? These are intuitive. This is the complex definition of a morphism of Posites. First of all, it's got to be a functor, so it has to be an order-preserving map. Second of all, it has to preserve covers, in a sense that if UI is a cover of U, then F of UI is a cover of F of U. And then there are two additional technical conditions, and these are translations into the context of posets of the conditions that I omitted previously. First of all, the image, we have a mapping from P to P prime. So that means that the image of P should be cofinal in P prime. And also for each U prime in P prime, the elements of P whose image exceeds U prime should be a filter. So technical conditions. Now, even these, everything I've said so far is just like a drive-by in a bus. Okay, you don't need to remember all of it, any of it, much, just to get the impression of it. A coverage on a meet semilattice Q is an assignment T, which to each element U of Q assigns a collection T of subsets called covers of U, such that if UI is a cover of U and V is in Q, then the collection V inf UI is a cover of V inf U. In other words, covers, right? In a meet semilattice, we just designate certain sets as covers, and we demand that the covers be stable under infima, under infs by arbitrary elements of semilattice. And a meet semilattice equipped with a coverage would be called an M-site. A Grothendieck coverage on a meet semilattice is a coverage in which all covers are downsets. And for each U and P, the downset of U is the cover of U. And here's the important condition. If R is in TU and S is a downset contained in down U, then S is a cover of U, provided that for each element of the original cover of U, right, the restrictions of S to that element are a cover of that element. So this is, we'll see where this condition plays a role in simplifying proofs in a few moments. A morphism of M sites is simply a meet semilattice morphism that preserves covers. It's that simple. So now let's, all right. So we have a very simple idea, and it's something like I mean, we're taking a meet semilattice, and then demanding that certain covers exist. We're gonna apply this in a moment. Yes.
Can you go back? Can you go?
So here's a rephrasing of the definitions that come directly from NLab. Let Q be a meet semilattice. A coverage on Q is a binary relation between Q and its power set that satisfies the following conditions, right? First of all, if V is a cover of U, then every element of V is less than or equal to U. And second, if V is a cover of U and W is in Q, then the elements W and V for little W in little v for little v in big V, right, is a cover of W in Q. And if this relation is a coverage on Q, we call the pair an M site. So this is just a change in vocabulary, but it makes for a very nice, nifty, and compact presentation of the axioms. An M site morphism from Q with its coverage to Q prime with its coverage is a meet semilattice morphism that preserves the relationship.
Link this to T of U. You link this to the T of
Where, am I on the right page here for you?
and next page.
Next page.
So how is this related to the T of U definition?
All right, those things, those V's, all right, those V's that can occupy this position with respect to U are T of U.
Okay.
Yeah.
T
T of U is equal to the set of all V's such that U triangle V. T of U is a set of all V's such that V covers U. It's freezing up. Okay, so those are the definitions. Now, with the definitions of M site in site, we will make a construction. An ideal of a site is a downset such that U is in I whenever U is covered by V and V is contained in I. That's a really natural condition. And a set of all ideals of S with its coverage is denoted by idle S. Now, it's clear that any intersection of ideals is an ideal. And therefore, the ideals of S is a complete lattice. The intersection of all ideals containing a given subset of S will be denoted by. Incidentally, I'm sorry that I changed notation here. I was talking about Q as a meet semilattice previously, and now I'm using S as a meet semilattice, so be warned. And then we have some theorems here. All right, so a couple of cautions. First of all, the downset of X needn't be an ideal. For example, consider the meet semilattice S, which is N union a top element in its natural order, where we say that M is covered by the downset of N if M is equal to N or M is equal to N plus 1. That is, the downset of N covers the element just above it, which is nutty, but right, it's consistent with the definition. And that's what we want to show what the definition means. Well, then the ideal generated by 0 is all of N. So every downset contains 0, so there's only one ideal here. So the problem, one of the problems lies in the fact that this coverage is not Grothendieck. There's a little argument here. It shows that if the cover were of N would not only cover N plus 1, but would have to cover N plus 2. and therefore n plus 3, and so on. Another caution is that the soup of a collection of ideals needn't be equal to the collection of all elements that are covered by some cover in the union of those ideals. Now, this is an argument that you use in dealing with ideals frequently, say in the context of frame theory, constructing algebraic frames. But again, the problem here lies in the fact that there's an example that shows that that fails right here, but I won't go into detail. But this is also related to the failure of the Grothendieck condition. Okay, now in considering ideals, here's a technical device that we want to use. Right, in algebra, there are always two ways of generating a sub-object. One from above, right, as an intersection of those elements that have a property, and the other one down from below. So you keep on including those things that are required in order to meet the closure condition that you want. So this is a technical device for generating ideals from the inside. How much time do we have now, Chip?
13 more minutes.
15 minutes, okay.
13.
All right, well, I mean, this is, we don't need the details here, but the idea here is that if you're trying to generate an ideal, there are certain things that you obviously need to throw in. But having thrown them in, right, you find out that there are other things that, as a consequence, will belong. So if you iterate this process of throwing in those things that you suppose ought to be there, eventually it stabilizes and you wind up with the ideal. So this is useful in proving the following. So for any site, now we prove that for any site, right, the site ideals form a frame. And we can come back to the proof if people are interested, but it's not surprising. And but just a comment, what we need to prove, the difficult part is proving that the lattice that we create is clearly a lattice, all right, clearly a complete lattice. The hard part is proving that it's distributive lattice. And here the site condition is what enables us to do that. The intersection lemma refers to the device that I used for constructing ideals. And it's another thing that I won't prove, but the prime here denotes throw in those things that you obviously need to throw in. So if I take two downsets and take their intersection and throw in the things that I obviously need to throw in, it's the same as the intersection of having thrown in all the things that I obviously need to throw in for D and all the things that I obviously need to throw in for E. On the other hand, the intersection of D prime and E prime is not D intersected with E prime, but it is D intersected with E prime prime. So if I throw in the things twice, I succeed. We can come back to the proof if needed. All right, and then from these, we get the, the following thing. First of all, every frame is a site where we take the canonical coverage. That is, we say that Y covers X if X is equal to the sup of Y. And then whenever a frame is regarded as a site, we assume that it has this coverage unless another is specified explicitly. And then the mapping from any site to its ideals, which takes an element to the ideal it generates. I suppose I should have put the triangle here in place of I. Well, that's a site morphism. And finally, we have a generalization of a theorem that appears early, or proposition that appears early in Johnstone's book on stone spaces. I think he has his sites are distributive. I think he does this when the site is a distributive lattice and the covers are the suprema. And the covers are the suprema. But suppose that F is a frame map. Suppose that F is a frame and phi is a morphism of sites from S to F. Then there is a unique frame morphism from the ideal frame of the site to F that composes with the embedding of S in F. We give P. And the proof is here, but the proof as on this slide is not correct because of things that I pointed out earlier in the talk that are appearing down here. Let's see here. This is not true in general, but this is fixable. Okay, well, that's I mean, I think that shows you that there's something at work here. What are some instances of sites? Okay. Marcus and Ram and people were looking at what are called weakly distributive semilattices, meet semilattices. And in a weakly distributive meet semilattice, those suprema, those finite suprema, or I guess those suprema that exist are stable under meets. Thus, the suprema that exist form a coverage. So that puts constructions with weakly distributive meet semilattices into this framework. Another construction is a construction of the injective hull of a meet semilattice, which is a frame. And what's the construction there? You just take the frame of all ideals?
No frame of
Admissible.
exact ideals, exactly.
Frame of what?
Exact ideals, that is.
Exactly.
Posed under distributive joints. Right, those are the joints which commute with binary meets.
Right, yeah, okay. So there's that, all right, so it's the same coverage, but it's in contrast with a weakly distributive lattice, all existing joins must be admissible. But in the case of the injective hull, the coverage is just those created by the admissible joints, right? So those two constructions fit into this context, and we hope to examine them from this perspective. So that's what I've been thinking about when I'm not shopping for donuts.
Kappa frame speed within this language.
You want to help?
Do you think that's on the horizon?
Yeah, I think it could be. I really don't understand what Annalisa and John have done. So the first thing I need to do is take a careful look at what they've done. Now I know that this equipment here is relevant to what she's been doing. So the first thing to do is to figure out, how much of this material they already have discovered. And then beyond that, there's a really fascinating construction that Barong uses in his major paper. So he starts off with an arbitrary distributive semilattice. and then makes it distributive by freely adjoining exact covers. So I'm going to say that, or in this case, exact co-covers, right? Because his construction is with adjoined semilattice. Another thing that we've noticed, Marcus and company, is how annoying it is that half the literature on semilattices is in the language of meet semilattices, and the other is in the language of joint semilattices. And then you need to translate back and forth. And some things are completely natural. The problem appears to me to be the fact that I forgot about the camera. The problem appears to me to be not the fact that there's any problem with dualizing, but that the English language ideal, right? Even the word ideal always means like a downset. But the ideals and the filters are a meet semilattice has ideals and filters, and a joint semilattice has ideals and filters. But the words are incompatible.
Always think of meet as multiplication and a join as an addition.
Yeah, exactly. You get the same problem with evaluation theory, all right? Where you have where the order of the value group is in some sense the opposite of the order that you expect in the ideals in the valuation, right? Okay, anyway.
Jim, you were not able to find your webpage on the Posites, but
Oh, found it. So. Yeah.
So I guess. So I understand movement is original motivation of defining sites was to be able to define comorbid groups in situations where ordinary size design will not be allowed. Right. So is there some interesting comorbid for those sites that you want to achieve
I suppose so. Well, I can't answer your question. I don't know. I mean, I think that what I described in the talk is all machinery. And machinery is not inherently interesting. Although, people spend a lot of time perfecting machinery, to be sure. So the real question would be, are there joint semilattices that arise in a situation where it would be interesting to study their cohomology? Or meet semilattices that arise in a situation where it would be interesting to study their cohomology. So if you really don't know the answer, then don't continue answering the question.
well, I guess that's it.